13, 4, and 5, the K constants, there's many of them, and Q. And the worksheet is kind of involved this time. Do number 23 AC, 26 A, B, F, and on the back do number 4 A and B. Now, I really wish I could say to do number 5, but 5 really is going to be the next chapter. But if you want to try and do it, you can. You'll get the answer key to it later. But hopefully I can remember to tell you about going over. We'll see it at some point. It's a really good problem. It might come back in the next chapter even. I don't know why. I just put it here. Okay. All right. So let me see. There are many kinds of equilibrium. I told you that every year equilibrium is always on the AP exam. For most of the 70 or 80 years of the AP, it was number 1 on the AP exam. Question number 1. Lately, the past few years, it hasn't been number 1. And the kind of questions they can ask you a question dealing with K or Kc. Remember, that's equilibrium with molarity values when you put brackets in it. Kp is when you put pressure. We talked about that. There's one called Ka for acids, Kb for base equilibrium, and Kw is water dissociation equilibrium, and then there's Ksp for solubility. Now, the good news, all of these from A down, we're talking about in the next chapter. So we're only doing these 2 in this chapter. But I'm going to show you how to get at least a little, I'm going to show you some of next chapter in this chapter because you can do it. It's not anything different. It's just different symbols. And it'll be a head start to help you in the next chapter as well. All right, so, for example, and then there's just 2 words, homogeneous, heterogeneous equilibrium. Well, homogeneous equilibrium means everything has the same symbol. Gas, 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 gas. Or aqueous, 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 aqueous. But when you have some that are gas and some that are solid, or gas, gas, liquid, liquid, then those are called heterogeneous. And remember, you never put liquids or solids in any equilibrium expression. And you either put only all gases or all aqueous items in your expression. Okay, here's an example. So on the 13.4 it says, write the K constant for this one. Calcium carbonate, number 1, going to calcium oxide, carbon dioxide. Well, if it's going to be K, it didn't say which K it was, so we'll say Kc, okay? By molarity, there's only one thing that has molarity there, and it's CO2. So it would just be the molarity of CO2 to the first power. Now, you wouldn't put calcium oxide, because it's a solid, and you wouldn't put calcium carbonate, because it's a solid. So that's it. It's just going to look like that. If you wanted to put Kp, it would be the partial pressure of CO2, to the first power. Okay? Number 2. Now, this is one we'll see in the next chapter. But silver chloride is a solid, and it is in equilibrium with the dissolved silver and chloride ion. This is called Ksp. It means solubility, and P means product. Solubility. Okay. You might remember from the solubility rules, AgCl does not dissolve in water. Well, all those rules we told you, they're a little bit not true. They dissolve a very small amount, but it's really small. And you'll find that out, again, in the next chapter more. But so the Ksp expression will be silver ion molarity to the first power times chloride molarity to the first power as well. And there's nothing on the bottom because it's a solid. So see, remember, it's products over reactant. Products over reactants, products over reactants. The reactants in both number 1 and 2, they're both solids, so they can't go in the expression. Okay, and then number 3, I'll just show you this now, the H2O. What actually happens, well, I'll just give it to you this way. H2O is in equilibrium, with H plus and OH negative. It's called the Kw, the dissociation constant of water. And you'll get H plus and OH negative. Well, I'll say more about it at a later date. It can also be written as this. Do I want to just tell you real quickly? Why not? Here's what really happens in that reaction. 2 water molecules bump into each other. One H2O pulls the H off of it, and it makes what's called H3O hydronium. And then if you take an H away from this, you get OH negative left behind. You can write that down if you want to. You're going to see it in the next chapter. I'll come back to it. But anyway, it was here. So this is all you'd have to write for the answer for that one. And I'm just showing you this to kind of get you ready for it for later on. All right. Then it says, oh, actually, I do have it. And number 4. So, yeah, I guess you will write what I just had. It does go on number 4. It's just an abbreviation, H3O, OH negative. I didn't know I taught it right there. Okay, and like I said, I'll tell you more about that in the next. That's called hydroxide. That's actually called hydronium. Hydronium ion. H+. Both of these are hydronium. This is probably more a better way to think of it, because the H really joins onto a water molecule. It's not sitting around freely. Okay, and then here's one. Number 5 says, what if I have HF going to H+ and F-? Well, this is an acid. Anytime that a substance on one side releases H+ on the other, that's an acid. So we call it Ka for acid. But the good news is you do it the same way as you do the molarity Ks. Kc, H+ and F negative. And they both have 1s. You don't have to worry about putting any number in there for that one. All right. Then, let me erase this and go to the other 2 here. So you'll have a bunch of these expressions to look back at. Six. All right, this is called acetic acid. This is actually vinegar, CH3COOH. It's another way to write vinegar. And it breaks off one H to give you chaku, hydronium and acetate. Okay? Remember, you may have seen that thing. Oh, yeah, that's why we did acetate that way. So the products are H+ and acetate. You can put COO negative. That's usually how we do it. And on the bottom, CH3COOH. Now, you can also write acetic acid as HC2H3O2. You could go there instead, and instead of acetate, you could put C2H3O2 negative. And they've used both on the AP before, but this is kind of a good form for organic acids. All right. Then number 6, this is a really good one. I'll write this reaction down. NH3, ammonia reacts with water to give you ammonium and hydroxide. Now, this is like the most important. You know what? I'm sorry. I've been standing in front of this, and I can tell now. Because I got some stuff on the floor here. My floor desk is getting in the way. Okay, this is a little bit better. Ammonia is a base. And this is the most famous, probably appeared more on the AP than any other base, okay, in equilibrium. Kb would be, all right, NH4, ammonium, times hydroxide, which has a negative there, over NH3. Now, you notice you do not put water because water is a liquid, okay? But water is needed in order for this to grab the H from it to make this dissociated ions. So that's what you get for the base. Now, let me show you another one. So NH3 is probably the most famous, most commonly occurring on the AP weak base. We're going to talk about bases and acids in the next chapter, but I'm going to show you a little bit here. Okay, an organic base. You remember NH2, the amine group? That would be aminomethane. Organic aminomethane. Aminomethane has NH2. Well, it has the same reaction with water. It's just going to grab an H from it to give you CH3, NH3 plus, and hydroxide. So, you know, you could do this. You could have aminomethane. It could be ethane, propane, butane, pentane, whatever. It could be CH3, CH2, 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 NH2. If you see the NH2 anywhere with a bunch of carbons, you know, then that's how it'll appear. I mean, okay. So anyway, it pulls the H off and gives you NH3 on this side. So NH3 gives you NH4. NH2 in organics can grab an H plus to give you NH3 plus. So that K base, it's also a base. This is probably the second most common thing, is that when you see some kind of organic group with an NH2 on it. This is the most common of the bases, and this might be maybe not, but it's a pretty common one. I've seen it more than one time on the AP. Okay, so CH3, NH3 plus goes on the top. with OH negative. And on the bottom, we'll go CH3NH2. Okay. Now, all right. So there's a little bit in there. You could read this about why do we not put solids and liquids in the expression? And it talks about there, we're only looking at concentrations or molarities, and we don't do molarities for solids and for gases or no, solids and liquids. Sorry, solids and liquids. But I'm just looking about silver chloride, but I don't think it's anything if the amount of AgCl is increased. Well, I guess I'll mention a little bit about that. And then I'm going to talk about Q. What is Q? What is Q? What is Q? Okay, let me just say this. I know what the most important thing is here about silver chloride. So this is back to something we'll see in the next chapter, but I'm going to tell you now because actually the problem that was on the worksheet, I said number 5, is you don't have to do it. Well, you don't, but it's going to be something you have to know for the AP. But I just wanted to show you about this. Okay, so the Ksp would be silver times chloride. Okay, I think we saw that one already. Well, what it's saying is, remember, if you have a saturated solution, what that means is I told you this before, all the silver and chlorides that can possibly dissolve are in there. You can't have any more. So if I increased and put more solid, it doesn't matter if this is an equilibrium and it has 20 grams of salt, and if I add more salt, it can't be any more. You can't have any more particles because no more can dissolve. It's saturated. Okay. All right. So adding solid, Le Chatelier, adding more solid in here. If you're at equilibrium, just say if we're at equilibrium already. If I add more AgCl, it will not do anything, no effect. However, if I were to increase the temperature, a higher temperature, maybe more will dissolve, then more can dissolve, and then that could increase it. But of course, that's a different constant. You'd have to see the kilojoules for that. Or if you did this, what was it saying? If I removed some chloride, then yes. Okay, so if I add salt, nothing will happen. But if I remove some chloride, then it is going to shift, like the little seesaw, it is going to have to shift to the right. So that solid amount will go down. It will shift right and it will decrease. Okay, that will happen. So if I were to do that little bit. Or if I added more silver in here, it's going to also shift to the left and more solid can be produced. So if you do something to this side, add or take away these, it's going to cause an out of balance one way or another, and then you're going to your shift can cause this to increase or decrease only by changing these two. All right, but again, we'll see that more in the next chapter. Okay, now let me see if I'm going to be able to get through. I might have to do 13.5 on a separate video. Yeah, I guess to be safe, I'll just do that. So that'll have the math part in it. Okay, in 1 second. Well, probably be like 20 or 30 minutes, I'll make the other video.